Hi, everybody, and welcome to our webinar for the launch of ToffeeX and for the launch of our new product. It's a pleasure to see many people subscribing and joining the webinar already. Hope I will make a good job. And another good pleasure, as Alejandro was mentioning, great pleasure is hosting this webinar with our partner and friends from Ricoh. They are online with us. There's Mark, Masato, and Enrico, and they will share with us their experience on using our platform and the value added to their product. But before we dive in, well, my name is Marco. I'm the CEO and co-founder of ToffeeX. For people who don't know us, about us, we are a software company. We develop generative design software for engineering design, and our strength is on physics like flow dynamics, heat exchange, and some chemical dynamics. Before jumping into the core of this webinar, let me give you a very brief overview of what you'll see next. We will start introducing our friends from Ricoh, their technology, and this will be as an intro to the value and the experience they have and they had by using ToffeeX. After that, I will share more about our vision, about the Toffee capabilities, about our tech, and about our application. Really, again, I want this to be an intro for then go hands-on. I want to give you an hands-on live demo, and I will show how to set a test case in our platform in ToffeeX. Also, really show how easy it is to set a design case for an heat exchanger by using our new platform, and show also how you can generate multiple different outputs from the software in different conditions, especially different working condition, manufacturing condition, and really how to build a design of experiment. So then we leave it to everybody. We will have a fireside chat with people from Ricoh, and then we'll open to questions from the audience. So throughout this presentation, any comment you feel free to add in the chat, but also any questions, feel free to add your question into the Q&A box, and we will take it from there. So now, without hesitation, I will leave it to Mark and to Masato. So guys, thanks again for joining us today for this webinar launch, and feel free to give a quick presentation of yourself, and yeah, really, the stage is yours. Thank you very much.
Thank you, Marco. Morning, everybody, or wherever you are in the world. Might be afternoon. My name's Mark Dickin. I'm the engineering manager for Ricoh 3D. Ricoh 3D's European business. Next slide, please. Thank you. For those who don't know Ricoh, we're a large manufacturing company. Our traditional business has been focused around photocopiers and consumables. But since COVID, we've reorganized and changed our focus to become a digital services company. We have over 80,000 employees in over 200 countries worldwide, with sales over 12 billion euros. The main areas of R&D are based in Japan, but also in the UK for certain areas. One of these areas is additive manufacturing, hence the collaboration with ToffeeX. So here you can see on the screen is a bit of an overview of Ricoh's 3D additive manufacturing portfolio. So our print service is placed in the center of the image. And what that is showing is how we are leveraging the big Ricoh, the support facilities such as, R&D, compliance, marketing, etc. We also then use our interactions from our customers to inform Ricoh of what the customer and the industry are asking for, so we can make better informed technology development decisions. We are a technical service provider and a company that develops technology as well. We then have 6 different AM related projects that we're currently working on alongside the print service. And they range from varying at different technology readiness levels. At the top, we have our metal binder jetting project, which is focused around aluminium printing. This is the key area of focus for the ToffeeX relationship. We also have a powder-based 3D composite process that we're working on, looking at conductive printing, etc., and high performance applications. In a process that's very similar to the metal binder jetting, we have a ceramic 3D printing project, looking at geothermal and high temperature applications. We also have a full color resin 3D printing initiative, initially focused around the dental industry, but we're also looking at different applications there for high detail and high accuracy component manufacture. We've also then developed a waterproof resin for a hydro generator project using the SLA process. And then also in the US, we have a very close relationship with the team in America, specializing in medical applications, scanning patient data, turning it into anatomical models to improve patient outcomes at the point of care in hospitals. And then finally from me today, Ricoh 3D, we're all about collaboration, hence this webinar with our partners, ToffeeX. We like this cyclical model here that I'm showing on the screen, where we can cultivate knowledge with our partners, our customers, and the marketplace, you guys, to create strategic collaborations, to redefine the boundaries of what's possible. As we know, our industry is ever evolving, and we don't believe that any one player can do everything. Collaboration and a sense of togetherness is extremely important, and that's what we're fostering. Thank you. That's all from me. Over to Masato.
Thanks, Mark, for introduction to Ricoh. And hello, everyone. My name is Masato from Japan. In this metal binder jetting project, I'm responsible for designing to maximize additive manufacturing values based on customer requirement. I have used ToffeeX about 1 year, and I'm happy to able to share experiences. Prior to the current role, I had worked in mechanical design of several printers for 10 years. Today, I'm going to share 2 topics about metal binder jetting vision and user experiences with ToffeeX. To begin, I will explain our metal binder jetting vision. Here is our vision. We aim, previous page, please. We aim to contribute to the realization of a decarbonized society. So component cooling, such as inverter, motor, and battery, is a key challenge in electrification. And in general, overcoming heating issue in these components is key to improving performance and efficiency. We believe these challenges can be addressed with our innovative binder jetting technology of aluminum components. Compared to the existing metal 3D printing method, such as SLM, binder jetting can offer higher productivity and is more suited for mass production. Aluminum alloys are extremely difficult materials to sinter, the final step in the binder jetting process, but we are working to address the issues with a unique sintering method. Next page, please. We aim to be a total solution provider from design and production to value creation to address the challenges our customers face. To achieve this, we are accumulating expertise in DFAM using ToffeeX and other software, providing support to optimize our customers' product design. And as I mentioned earlier, binder jetting involves multiple processes such as sintering in addition to the printing process. There are our visions, and I will also share the technical to futures. First, I'd like to highlight our aluminum sintering technology. aluminum powder is known to be difficult to sinter due to the oxide film. So we are developing a unique sintering method based on liquid phase sintering process. As the left image shows, first we create green bodies with specially formulated aluminum alloy powders and control the amount of liquid phase to break the surface oxide. Finally, we can obtain high density sintered parts. This right picture shows there are almost no voids. Next page, please. The second feature is our excess powder removal technology. Our intelligent binder and solvent solution can create industry-leading complex and fine tube structures. The left picture shows a batch process where excess powder is removed by immersing it in the solvent with easy operation. The right picture shows after repowdering. These depths are more than 50 millimeters, and it's evident that even with a diameter of 2 millimeters, it penetrates through the internal channels. Yeah, next page, please. Yeah, these are the technical features. And finally, let me share our experiences with ToffeeX. This is a case study of water-cooled heatsink. Compared to the traditional M-flow path as a conventional design, we have proposed a heatsink with gyroid structure. By utilizing ToffeeX, we have significantly expanded the possibility of design, enabling us to provide our customers with more functional design models. And by just inputting design domains and boundary conditions, we can obtain the optimized flow path. Yeah, and I'd also like to share the quality of our sintered body. There are no defects on the outside, but this does not show the internal geometry, so we confirm the interior by X-ray observation. The result confirms that the complex internal channels can be reproduced, and there are no excess powders in all cross sections, upper, center, and lower. Yeah, here performance simulation result. We evaluated thermal resistance and pressure losses. The blue and left axis is thermal resistance. The yellow and right axis is pressure losses. Lower values for these mean better performance as a heatsink. Both gyroid structure and topology optimized structure by ToffeeX significantly outperform the M-flow path. In particular, the structure of ToffeeX shows significant improvement with reduction in pressure losses by 48%. And ToffeeX can also easily adjust it to optimize the ratio between heat exchange performance and pressure losses. So we can realize optimized designs tailored to various requirements from our customers. Yeah, this is last slide. I will also introduce a case study of an air-cooled heatsink, which was previously showcased in another ToffeeX webinar. In this case as well, only the design domain and boundary conditions were inputted, and our binder jetting components faithfully reproduce the CAD shape. Here, the heat transfer coefficient is compared and show a 31% improvement over the conventional heatsink, indicating efficient heat exchange performance. Next page, please. Yeah, that concludes our presentation. ToffeeX is a very powerful design tool and can easily output excellent designs. And with our binder jetting technology, we were able to convert it from digital to real. Yeah, thank you so much for your attention.
Thank you very much. Thank you very much, Masato. Thank you, Mark, for the presentation and for sharing your experience using our platform. Let's move now a bit more on our company, on our technology, and our vision. Thank you very much for sharing your vision on adopting additive manufacturing and adopting additive manufacturing for a wider, let's say, landscape of electrification. We share that vision, we support that vision, and more in general, we support the energy transition. And we want to help, we want to enable enterprises to find design solution, design for components to get to efficient electrification application, to hydrogen technology, for example, and more like carbon capture. So before moving on, many of you may know that we changed our name from ToffeeM to ToffeeX, and this is really to emphasize our vision. We want to embrace, we want to expand our capabilities, and not only and showing how generative design is not only for additive manufacturing. We don't want to limit ourselves to AM, but we want to expand, helping all the industries, regardless the manufacturing method. So it's about changing the way components and efficient solutions are designed without changing the way they are manufacturing. How to enable this, we build our platform to support this transition, to enable engineering to design more efficient thermal management system. We believe the experience should be as easy as possible for our user. We envision the future of engineering design, and the process by using Toffee we really looks like this I'm showing now. So it's about importing what are the main design constraints, the main rough space when I want my component to be designed, and then leaving the optimization to the software, which again is simulation driven, it's physics driven. So it's going to simulate the physics of the problem and take an informed decision to generate the optimized design. And then it integrates easily with your existing workflow. This is very important part of our vision. The user don't need to be an expert. They do need to be an expert of flow dynamics, for example, to use our software. But let's go a bit more hands-on. We prepare a demo to show how the software works. Before jumping into the demo, what I'm gonna do in the demo. So I'm gonna show how to set the optimization of a liquid-cooled heatsink. The shape I'm going to optimize is the one you see on the here now on screen. This is like the external shape, the external box I want to optimize. So I want to generate all the internal structure for this component to be as efficient as possible to extract heat from the bottom layer. And by using a liquid flow, entering one of the two holes and exiting the other hole. I'm going to start by showing the capabilities of our platform. I'm generating optimized design in 3D, so suitable for additive manufacturing. I want to emphasize how, within the space of additive manufacturing, we can control the manufacturing constraints. For example, the overhang angle. If I want to minimize or reduce to zero the region that needs support during the printing, I can input literally in my software the overhang constraints. So what is the maximum degree of overhang the software will allow during the generation of the optimized design. But more, I will extend more, and I will, let's say, show also how on the same test case, Toffee can produce design that are not only suitable for additive manufacturing, but they can be produced with more traditional manufacturing technique, for example, tooling. And even within the more traditional manufacturing technique, you can play with more specific manufacturing constraints. For example, the machining tool size. And here a comparison, but I will show much more during the live demo. this was really to underline how, to emphasize how with Toffee you can really create a design of experiment. What does it mean? On the same test case, I can optimize, I can define, I can generate my optimized shape by taking into account different possible outcome and different requirement for my manufacturing method. In the example, I can leave the software completely free to create the most intricate structure, which is the first column, and not surprisingly is the most efficient. But then it might not be efficient on an overall workflow and production workflow. So I can add my manufacturing constraints. In the example, the overhang of 45 degrees, or a stronger manufacturing constraint for the machining for 1 millimeter and 4 millimeter tooling. And this is obviously reflecting on the efficiency, but the value we are giving to the customer is the possibility to the customers to pick what is the best design and to navigate across optimal design and then choosing the one of interest for the purpose. Now, let me move to the platform and show a bit more. Everybody seems so. Let's see. This is how you would see our platform as soon as you log in. We are native based, so everything is hosted on cloud and leveraging ACP computing. When you open our platform, you land into the project page. I want to create something. This is my project. In this case, I want to create a liquid-cooled heatsink that I just showed. So I enter my project, and what is pretty obvious, I would say, I upload a domain. In this case, you can see here, I upload a domain in a very easy way, and it automatically identifying and recognize the surfaces to then identify, for example, boundary condition and to ease the process of setting more downstream. What is really important for each domain, I want to define a toolbox. What is a toolbox? A toolbox is the environment, the space where literally I will spend most of my time. Is the environment where I pick my physics, I pick my simulation, I pick my design requirement. So let's create a toolbox and let's set together our optimization. So let's create an heat exchanger 3D. This is what you see when you want to set up your simulation. This is my domain. I halved my domain to ease the visualization during the setting. And I want to create something. And this phase of creation, we call it a run. So let me create a run. And I want to create a design. I can also just simulate the physics on it. But really, the value I'm going to show today is how to optimize a design. Let me create a design. Now it's automatically asking me to populate what are my design setting, which is really the family of the collection of requirements I want from my design. Then it's going to ask me, what is the physics you want to be the base, the physics that's going to drive this optimization, and obviously the mesh, because it's a numeric simulation. Let's start from the design. What is really important is to set what I'm optimizing for. In this case, I want to minimize the pressure losses in a more general multi-objective optimization, meaning I want to balance the optimization of pressure losses and heat transfer. So I'm going to minimize the pressure losses and maximizing the heat extraction from the bottom. Being a multi-objective optimization, I want to define also what is the relative importance of one objective against the other. So I'm going to decide some weights this is up to the customers to define this relative importance, which in this case, I'll just put 1 and 1. Then you have more design constraints, but really for the purpose of this, let's focus on the manufacturing constraints of additive. You have the most general one, the minimum feature size, the channel clearance, but let's see a bit more on the overhang. You can obviously specify the angle. Let's put 45 degrees. You need a direction of the building direction. And you need also the surface where you're gonna start the printing from. The hot wall is the bottom wall. All the naming happened even if I didn't show during the definition of the domain. Let's update this. I know for people of expert of additive manufacturing, it's not really meaningful to print in this direction, but for the purpose of please allow me for the purpose of this webinar. Then you have further constraints for the machining, like the tooling size, etc. Now, you can even specify locally by using volume these design constraints, but this is a bit out of the interest of this. So let's jump into the simulation. So this is very familiar for people using CAE tool. So it's about defining the properties of the fluids, of the solid, and really defining the set of boundary conditions that are describing my flow and hence my physics inside the volume. So let's start. I will have an inlet. This is already named, and I will specify in an inlet my velocity and let's say a temperature. And there we go for the setting of the inlet. Then what is very important is the definition of my heat source. There are many ways, more or less equivalent to define. So you can define a heat source from a volume, for example, in the optimization of a coolant system for a CPU. Or in this case, let's keep it easy. Let's define a fixed value for the temperature. Let's put 400 degrees, for example. And I'm gonna put this on what I called the hot wall. So I'm for ease the visualization, also to guarantee the symmetry of the component, I'm going to define the symmetry wall here. And then what is important, what is left is the outlet, which is already pre-populated because it must be compatible with the other boundary condition, and the wall, which I will easily set as adiabatic, zero gradient. All the remaining wall are set. So you see when everything is compatible and is properly set, green light, let's go. Fluid properties, easy, let's pick this liquid. The customers can really input all the fluid features he wants. For the solid, let's keep aluminum, which is the same I showed you earlier. But again, also for the solid, the customers is free to, the user, sorry, is free to add any property. So the simulation is set. The mesh, I won't spend time here. Very straightforward, very common for most of you. You can pick a number of cells. You can pick the size of the cells. You can make refinement, boundary layer, etc. Once everything is set, everything is compatible. So the software now has the design requirement, the physics I want to use to drive my simulation, and the mesh. So now let's start. As I said, native-based, setting up the machine on the cloud, creating the mesh, creating the simulation, using the simulation for the design, and complete. At the end of the simulation, you will be able to visualize and also to download the design, the simulations, and the mesh. This is it will take roughly 1 or 2 hours. So we already run these cases. And let's see the additive manufacturing one. Let's start from the unconstrained design. There we go. This is the optimized shape that you will see at the end. As I said, I ran on a slice, slice enough to see what's happening inside. And you have the viewer controls to play a bit. I really want to show you the fluid and showing how using physics-driven generative design, it's really creating an intricate component that are really the key to increase the efficiency. So the fluid enter from the inlet. It's breaking into all these small channel, and once it gets warm against the hot wall, is reconvected out to leave then the component. This is done in an efficient way because it's balanced with the pressure losses. So you won't see a big recirculation region. You won't see, let's say, a sharp corner, because the fluid, the optimization is driven really by the streamlines of the optimization. This is guaranteeing high efficiency in thermal extraction by maintaining very low the pressure losses. I want to show what happened when you add the overhang constraints. We've been particularly harsh on showing the degree. Let's do the same. Let's see the fluid inside and remove the solid. So yeah, we input here 65 degrees. So as you see, during the optimization, the fluid, let's say the solid, don't want to create, let's say, region that are in overhang. We have been particularly extreme here, so 65-degree overhang, we are kind of getting close to 2D extruded shape. Talking about 2D, let's go and show also what would be machining suitable design. As I show already in the presentation, we ran it for tooling size 1 millimeter, 4 millimeter. This is really what you would see from loading the file. Let's give it a few seconds. Oh, sorry. There we go. Really heavy. There we go. So this is what you will get at the end of the optimization for the 4 millimeter tooling size machining. Similar, you can play with the flow, visualizing the flow, etc. But you can download this digital file, you can download the simulation, the meshing, etc. So again, this wanted to be showing how easy is for really everybody, without being an expert, to set a simulation for an optimization of, in this case, a liquid-cooled heat sink under manufacturing constraints, under, let's say, the constraints of your existing manufacturing method. So now it's time to open a fireside chat with our friends from Ricoh. Please allow me 1 second to share again my presentation. So hope everybody can see the screen again, the monitor, okay? Mm-hmm. Yeah. So yeah, thank you very much again, Masato and Enrico, to join us today. So we would like now to open, let's say, a discussion about really your experience and the value added from Toffee to our product. Enrico, thanks for joining us. I will start straight with the first question. It's like, how do you think the generative design tools are actually helping the 3D printing business today?
Hi, everyone. Just by the way, a quick introduction about myself.
Thanks.
First. I'm one of the senior engineers here at Ricoh, working both on supporting the team with the metal binder jetting development and also with the printing service we offer here from the UK. We'll say in terms of how the software is helping our 3D printing business, when it comes to the metal binder jetting technology, it's really down to helping our customer, not just, we are exploring new application with our new technology, and it's not just about printing. As Masato said during the webinar, we want to be provide a full solution to our customer. So having access to this type of tool is enabling us to also supporting our customer with the development of more efficient and more effective design for their application. So by knowing what they want to achieve, we can also support them in creating the right design for the right application, especially as Masato mentioned during the webinar, a lot of the application we are targeting involves fluid management. And so the ToffeeX solution is really the right solution to support this application. And very similar, this is also applicable to our print service business. Again, some of the customer we are supporting with our print part service operate in sectors where fluid management application are really key. And again, being able to offer solution in terms of design are an added value for those customers, and provide an added value than just printing parts.
That's great, Enrico. Thank you very much for sharing both on the vision, on the direction, but also much closer, let's say, testimonial on the user, on your customer experience and the value you're adding to them. But more, a bit more on the, let's say, on the adoption also of ToffeeX. Probably. Maybe it's a question more suitable for Masato, which is the main user of ToffeeX. It's like how ToffeeX integrate with your existing processes.
ToffeeX is used as a DFAM to improve functionality. Now we are also modifying the model for successful sintering as an additional design process. But I believe in the future, we can apply the new function of manufacturing constraints, as Marco explained, to our binder jetting as well. So we will simplify the design workflow. Yeah, that's it.
Yeah, thank you, Masato. So in this, what did you like the most? What is the feature you like? What did you like the most about using ToffeeX?
The most that means the most interesting function.
Mm-hmm.
So
what do you like the most of using ToffeeX?
Yeah, I understand. At least I can raise three benefits. The first point is incredible fast computational time. I have experience with topology optimization of structural component, but I had understood that topology optimization for thermal fluids was still at an academic stage. The cases I introduced this time were all completed within a few hours, and this was the most surprising point for me. The second point is software can be handled even by non-experts. As I mentioned, my specialty is mechanical design, and I'm not an expert in thermal fluids, but I was able to learn how to use ToffeeX in a short period, about 2 or 3 weeks. It seems that conditions were set to be as simple as possible, I think. The third point is solo support. Any questions were resolved quickly via email or web chat. The software updates also incorporate our request quickly.
Yeah, that's great, Masato. Thank you very much for this. And are you planning to use any of the new features for your design activities?
I'm so interested in the functionality of manufacturing constraints, like overhang constraints. The manufacturing constraints can further simplify our current design process, which would be a significant benefit for me and our customers.
Great. Thank you, Masato. Thank you for taking this question really on the usage, on your experience of using the software. So maybe a bit more on a general topic. So for both of you, like more in general, how do you see, let's say, the generative design evolution, the generative design landscape evolving in engineering?
Maybe I go first. Just
Thanks.
couple of points from me, some idea. I think first thing is probably the computational power is something that we probably see evolving in future, speeding up this iterative process, and so the user can be focusing more on defining the problems, and the software will be there to sort of, again, it's a bit of a co-creation process where the software, by speeding up the process, will help coming with the right design, optimized design in quicker time, and again speeding up the development process of new products or more performing product. And I think we see the evolution of your tool, you know, going for purely an AM tool to considering more traditional processes. And I think going forward, it will be, you know, really nice to see integrating other decision-making factors into the software, like, for example, a cost analysis or a life cycle analysis of the product. And I think this is really something that, again, we probably see more in future, where the metrics will not based purely on physics and the outcome in terms of optimization, but we have a more global picture that will help the user decide which is the most appropriate solution, not just from a performance point of view, but also from a cost perspective and from a end-to-end life cycle analysis.
Yeah. Great, Enrico. Thank you very much. This is really, let's say, aligned with our vision. We believe that finding an optimal design, as you said, is not only about finding the best balance between pressure losses, heat exchange, or manufacturing technique, but it needs another layer. It needs also really balancing cost of manufacturing and operational costs. So the efficiency, physics, strict efficiency has to balance also with the efficiency of producing or manufacturing go to market. So adding a tooling tool for costing evaluation will give a much broader and comprehensive and informed, let's say, design of experiment. So for the user to pick the best one. Yeah, and Masato, what do you think about also this, the evolution in the landscape of additive manufacturing for engineering?
It's a bit difficult question for me. Generative design is an innovative technology that significantly lower the barriers to entry in engineering. And personally, as I mentioned, having experienced higher barriers in the field of thermal fluids, but generative design has enabled me to actively engage in this area. Yeah, that's it.
Yeah, thank you for this as well. Again, very aligned with what we believe, that generative design enable yes, the transition and adopting new design, but it's really on the user experience, so the possibility of enabling and giving to the user a wider capability, a wider control over the design workflow. Thank you very much, Enrico. Thank you very much, Masato.